Hello and welcome to another episode of Better Together at Science with Shinrai Sensei. And today we're going to be covering the electromagnetic spectrum, EMS for short, right? So, the electromagnetic spectrum, it combines things that might not otherwise seem related, like visible light with X-rays, with microwaves, and with heat itself, right? So, things that don't really seem like they should be related are all related because they are a form of radiation, which is a electromagnetic energy that we call electromagnetic energy, right? And the electromagnetic energy forms not only the visible light spectrum, which is a very narrow bandwidth that we can see. Obviously, that's why it's called the visible light spectrum. It's a very narrow portion of the electromagnetic spectrum, right? And then it also has energy that we can't see, but has a strong effect on us. So, like gamma radiation will almost definitely kill you. In fact, I highly doubt there's anybody out there that could survive gamma radiation, right? Whereas infrared radiation is what we experience as the sensation of heat, right? And so things that don't necessarily seem like they are related are actually related in the form that they are electromagnetic energy that is on the electromagnetic spectrum, right? So, the electromagnetic spectrum, the most proper way to demonstrate the electromagnetic spectrum, rather than showing a rainbow with like extremely dark blues and almost purple on this end, and then like extremely dark reds, almost, burgundy on this end, the better way to demonstrate the electromagnetic spectrum is actually to show a frequency wave. Because the electromagnetic spectrum is not so much about light being a particle, but light being a wave, right? And so the wave function of the light that we see and we don't see is the more important aspect that makes up the electromagnetic spectrum. So let's say the visible light spectrum is here. And we'll go ahead and we'll say visible light, right? So that's the visible light spectrum. Out of all of this, we can only see that much. And this end, you have like on the very end here, the very extreme energy, extreme frequency light on this end is called gamma ray radiation. Or, sorry, gamma radiation, I should say. Because gamma rays are from like a gamma ray burst, which is a type of star event. And then you also have X-rays on this end of the spectrum as well. And both of these we know are higher frequency and higher energy because they are capable of penetrating things that we think are opaque. Opaque being the term for, not light not being able to pass through. But opaque only applies to the visible light spectrum, right? So I cannot see through a tree that's standing right next to me. I can't see through the shelf, right? But if I was to fire an X-ray at this shelf, whatever metal objects are in this shelf, or bones, something more solid than, let's say, the wood or soft tissue are, will pop up on the X-ray as obstacles that it reflects back. So the X-rays that we use are more akin to like a radar system. You're trying to detect something solid while ignoring all the soft stuff, right? And so it's like actually more akin to sonar, I suppose, because you're trying to ignore all the water around you and you're trying to focus on just the things that are more dense than the water around you. So you're trying to find like animals, or you're trying to find ships, submarines, things like that. That's X-ray would be more akin to sonar, right? Gamma radiation is incredibly high energy, and it's most famous for in like Marvel and stuff like that. Gamma radiation is what the Hulk's most famous for. Well, in reality, if you get struck with gamma radiation, you're not turning into the Hulk. You're turning into a corpse. Because gamma radiation is so high energy and high frequency that you don't know that you got hit with it necessarily. You can have a gamma ray burst that's hundreds of thousands of light years away. And if that gamma ray burst is just angled at the right angle that it passes through Earth, right? It fires directly towards Earth. That gamma ray burst is going to kill everything on the planet because it destroys DNA molecules, right? It completely rips apart DNA. So gamma radiation, X-rays are on the higher frequency, higher energy, and it obviously makes sense that the higher frequency would be higher energy too. The lower frequency, lower energy, this is where you get your microwaves and your infrared. And infra is a prefix that means lower or below anyway. So infrared is a very apt name for that energy anyway. So your microwave radiation, oh, sorry, I spelled microwave. I was writing a little too fast, kind of got ahead of myself. So microwave radiation and infrared radiation, they more pass off heat, and they're too weak to do much other than heat things up a little bit. So you can kind of feel them, but you can't really get much damage from these other than over long periods of exposure, because due to the fact that they're much lower frequency, that means there's fewer particles moving into and out of the object at once, right? So the particles aren't moving as quickly, nor are there as many of them as close together. So the photons will not pass as much energy as these light rays over here. And also, I'm going to write UV here because UV is also on that end. And so all of these are different types of light, but they're also different types of energy that we can measure and we can see, right? We can see gamma radiation if we just tune satellites and the computers that monitor the satellites to the right frequency of photon. We can see gamma rays, we can see X-rays, we can see UV, we can see obviously visible light, we can see all of that. Microwaves we can see, and infrared we can see, right? And it's actually because of the Doppler effect, which I'm kind of covering something else here. The Doppler effect is where when something's moving towards you, the sound waves or the waves of whatever it is will compress, and as it's moving away from you, the waves will lengthen, right? And the Doppler effect is actually what led us to the discovery that the universe, at least as far as we can observe and as far as we can understand, the universe is theoretically expanding. And so it's because we saw more infrared, microwave, and, more of a red tint, or the red shift, as it is colloquially, oh my gosh, I'm having trouble with the word. So it is known as the red shift, and the man that the Hubble telescope was named for, Alfred Hubble, he saw that the red shift was occurring, and he's the reason that we have the understanding today that the universe must be expanding, and theoretically is expanding at an accelerated rate. So that means that it's accelerating in its expansion, right? But the electromagnetic spectrum, this is the best representation that you can have for it. Visible light right here in the close to middle. Microwave radiation over here, just a little bit past the visible light, and infrared over here towards the end, right? And then on the higher frequency end, you have UV, then X-ray, then gamma. Obviously, there are a lot more types of light and energy that I don't have marked up here. I think these are the more important ones, though, because it gives you kind of an idea, right? So the electromagnetic spectrum, best represented by a frequency wave that gradually expands and the frequency gets lower, as well as the waves and the crests get lower, right? That's another thing you'll notice. As frequencies usually get higher, the crests and troughs of the wave get higher. And then as frequencies get lower, the crest and the trough get lower, because the wave is trying to maintain forward momentum. It will try to keep its speed. And this is more in reference to light, but I suppose you could say the same about anything. But they're trying to maintain the same speed. All of these light particles are going to try and maintain the same speed. And that's why they're getting too many of them going the same speed when it comes to gamma radiation, right? They're all going the same speed, but they're a lot of them close together. And so they compress and they move higher and lower because they are trying to go faster than they can go with something in their way, right? Something blocking them, which is the upper limit of the speed of light, right? And then as you go further this way, they're still trying to go the same speed, but they're not as close together, so they can move more forward and less up and down. The up and down motion of the wave is usually more because it's compressing because of some obstacle or something is blocking the fluidity of motion forward. So they move more up and down because it's trying to transfer the energy forward, but it can't, so it comes up. Which we'll get into wave mechanics in another episode, right? But I think that's where we should leave the electromagnetic spectrum today. I am having all sorts of tongue twisters today. So the electromagnetic spectrum, this is kind of where we'll leave it off today. Like I said, represented as a wave function and show that visible light here close to the middle, but not exactly the middle. And then on this end, you have microwave and infrared. This end, you have UV, X-ray, and gamma radiation. All right, so if you guys have any questions, please leave them in the comments section below. I look forward to seeing you guys in the next one, and peace.